Hey everyone, my name is Eric Vasquez. I'm with the Relectric Car Team here at the University of Central Florida. This is going to be a super quick, I'm not going to say super quick, it's going to be a bit dragged out tutorial on how you can do your own motor mount and simulate the stress that it will face in the car. This is just weight, like static stress analysis. This isn't anything dynamic or torsional. This is just super basic to see, okay, can it support the weight of the vehicle? And this one I'm just going to be super basic with you. It's going to be something that's like, okay, I know this is going to work because it's super solid, made of strong material, super thick. Like, you won't have to worry about this breaking, but it'll make it easier for you to understand, interpret some of the stuff you see here. So what I'll show you first is you're probably looking at this and saying, what am I looking at? What is this? I'll first off open up the model, show you our motor mount, and then you're wondering what this is, and this is actually just part of the chassis that I modeled previously. So if we grab the scanned vehicle, you can see it closely blends in with some of the material here. Over here, this is all engine and components of the vehicle. This is the walls of the chassis, and this part here is just another component of the vehicle. So I am almost confident that underneath this component it looks similar to this, but we won't likely be using this for mounting unless, who knows, maybe someone has an idea and they want to do that. By all means, go ahead. But this is something for you to look at. As you can see, I try to line up the motor as best as I could with the present engine, so I can line up the axle so we know where it's going to be located. So now I'll hide this, and if I go over here into the static stress, I'll just show you guys what it basically looks like at the end of it. So after adding material, fixtures, different situational things that you would try to associate with real life with mounting a motor, we got results like this. This is just the stress, so it's showing you like points in your design where it's going to be facing the most stress. I assume this was fixed, but it's going to go through some stress distributed around this surface, as well the back of the motor onto the plate is also going to face some stresses because that's the only area where mounting or screwing the mount to the motor, as well as the edge here because of the weight of the actual motor itself. Gives you a rough base number of pressure or stress that it's facing. And if I go to displacement, you can see the displacement of the actual motor mount because, you know, weight of the motor, there's nothing supporting this edge, so naturally it's just going to want to slope down. But this is super deformed. Solidworks typically deforms this to an extreme so you can see it better. But if you click over here, its units are in millimeters, so it's really a 0.01 millimeter of a displacement. So it's very slight, very small. So that's how you know this design does work, but it can be costly. So if I pull up some information on the material, some of the side railings can cost $10, which isn't bad. Some rods that are maybe an inch thick can cost maybe $40. The sheets of aluminum, this is only like 1/4 of an inch, so it's not even the full inch in this design. And with 1/4 of an inch, it already exceeds around like $120. So you imagine 4 times the amount. That's like almost $400, $500. It's insane. So you're definitely going to want to optimize this as much as you want. This is just a design for basic terms or basic tutorial purposes. So I will now go over step by step what I did to design this, and then I will try to remodel exactly what I did to get to this point. So let's first start off where I was. So first thing you do is draw your design. Have an idea, you have an image, there's uploaded images of the chassis. If you want a 3D scan model, that's also uploaded on Teams and on Fusion 360. So we already had a team meeting on designing this and what some people had as ideas. One was directly just screw or bolt the motor to the side of the chassis directly. No hesitation on that. Another one is similar to the design we're doing here, but it doesn't have a bottom plate. It's just a back plate with 2 rails coming along the sides. And like a U bracket. And then there's another design similar to what I have here, but it has extra dampeners. It's super expensive. There's no point in having something this extreme because we're trying to optimize. We're not trying to go above and beyond. We don't have all that money for that. So we're going to go with that design. We have it in mind. Next thing that I would do is open two folders or two files. First one is going to be the motor itself, and then just a brand new part file to start designing. Another option would be copying this file and saving it as a different file, or what you can call it, the motor mount file, and then use these parts to design around. So what I mean by that is I can easily create a new sketch in this part file, convert entities, right click, and now I have exact dimensions on the motor, and I can design around it. And this would make your life a lot easier. So like if I go over here, I convert more entities, I can go here, here, here. I can just now go here, parallel to this face, and I can actually start mounting along the edges here. Let's say I want to leave clearance for these little through-hole circles. I can do that because I can ignore it. And what I could do next is simply remove all the other annoyances and clearances that don't really matter in my design. I can keep going. It doesn't matter. It doesn't matter. It doesn't matter. None of this matters here. This is super quick, super basic, very rough. Look at that. We have a plate that avoids these two screw holes on the motor. So, you know, that's something you can do. For now, I'm just going to delete that. I don't want that. Or the second option, which is what I did, is I took measurements around the whole thing, and then I would go step by step on recreating it and modeling around it as best as I could. And you can even in the future move on to redesigning it in the assembly. So yeah, super quick. That's one way of doing it. Super easy. As soon as you're done creating your your motor mount, I would do one extra step if you forgot to do it already, is I would take all your dimensions where your motor is going to be sitting and increase the size. What I mean by that is, you know, the back plate of the motor is going to be facing this wall, you know it's going to be sitting here, and these two walls are going to be hugging the motor on its side. That's the design I'm going for. So what I did was I increased those dimensions by 0.1 millimeters. So I have a little bit of clearance just in case milling is inaccurate, because a lot of times nothing's going to be exactly the way you want to manufacture it. So you want to oversize it slightly, because you can always add more material and then try to like squeeze it in using putty or anything else. But it's harder to try to fit something that is too small for your part. So over here, the actual dimension was 245, so I increased it by 0.1. And this length here, I decreased a bit so I can avoid some surface areas. But it's something to keep it in mind. So then I will go into assembly. Yeah, fix the changes. We'll go into assembly, and then after opening an assembly, I would start mating everything together. So I would go to assembly, I'd go to mates, and then make sure that this is fixed, your chassis, make sure it's fixed. I would also hide this scan model, because if you try to work with it, your computer is very likely to crash, because it is a lot of different numbers it's trying to calculate. It's super like abstract, it's not very concise, like it's very hard for your computer to keep up with modeling that, so I just hide it. I mated the surfaces of how I wanted to mate it, so it's an initial position of where I want it to be. And then to help reference understanding where it's going to be located in the engine bay, you can unhide the scan model and try to line it up with the engine. So I'm not sure if you can tell, but this here is the scan model of the engine. And I tried to line it up as best as I could so I know exactly where it would lie within the chassis. So now I'm going to hide this. It would line up here. I don't see any clearance issues here. It's not contacting these. I do see this here, but this you can remove. We can remove in the after process, so don't even want to worry about that. Once you have everything initially set, you want it moved exactly where you want it to, you can now go into simulation and then new study. And if you don't have simulation, you go to tools, add-ins, and then turn on simulation from there. But I would just run a new study. And then add in different types of supports, materials, step by step. But I'll rerun it through with you guys so you can understand what I did. So I'll run a new study, static study, yes. First thing I do is go to my parts, and then I would select these three here. One thing that you want to do is select your scan surface and then exclude from analysis, because that leads to a lot of issues. Just exclude it from the analysis completely. This is included because it's solid geometry. The mount's included and the motor's included. These are all solid geometries. They're not too hard to calculate. You're good. Once you're in there, you can start adding materials. Here, I can just give this whatever I want. I don't think it matters for the motor too much. The mounts and the body do matter. So for the body, something solid that I believe is a similar material we can use is either alloy steel SS, or maybe even, no, aluminum. We can go 1080 aluminum or 6061. I believe 2024 is used in vehicle chassis. I'm not entirely sure, but for now, that's what we're going to go with. And for the, mount, you can look at different websites. If I go to Chrome, the plate that I was looking at is 6061 aluminum. So I'm just going to make the entire thing that. So I'm going to go here, 6061 T6. That has its own material. This has its own material. The weight on the motor, I already modified it, so you don't have to worry about that on the file. But in case you're wondering how to do that, you'd go to evaluate, mass measurement, delete the model assembly, click on your motor, override the mass, and 200.62 pounds should be the mass of the motor. So, first part in static stress analysis is done. We've added material. Next thing up are connections, fixtures. So, let's go over here. We're going to add first contacts because we don't want things to blend into one another. So we're going to do component contact, select all three. Do no penetration, check. So now there's a contact between all three of these, so that nothing's going to blend in with each other on accident or merge, because that wouldn't happen in real life. No two materials are just going to merge from physical stress like that. Next thing I'm going to do is right click on connections again. I'm going to go to rigid connections because it's the easiest thing to work with. And I'm going to, I guess, weld or fix or bolt my motor mount and my motor. So I'm imagining how I'm actually going to attach this. The way I was thinking is welding it or bolting the motor mount on the top edge to the chassis, and as well as the side of the chassis to the back of the motor mount. So first thing I'm going to do is select this area. Click on the next box, right click, select other, and then now I selected the bottom surface of this. You can see the pink outline, the bottom surface of the motor mount. So that's selected. Those are connected now. That's a fixed ridge. I'm going to do another ridge connection. I'm going to imagine that this whole side of the chassis is going to connect to the back plate of the motor mount. Another solid ridge. One other one is I'm imagining that there's going to be bolts connecting from the motor mount to the actual motor on the back side of this. So that is the last physical connection I'm going to include here. So I'm going to right click on connections again. We're going to click rigid connection because it's the easiest to model. We're going to click, I'm going to do select other first. I'm going to click the back plate. You can see the highlighted geometry of the back of the motor. And then click on the pink section box here, back plate of the motor. And now I have fixed geometry on the back of the motor mount to the chassis, top of the motor mount to the chassis, back of the motor to the side of the chassis, and those are the only places we're going to be bolting it to or welding to, depending on what you have in mind for your design. Next thing we're going to do is add a fixture geometry. So this thing is not just going to be floating in mid-air. So we're going to say that the bottom of this is going to be fixed and will not move under any circumstance or morph under any circumstance. Next thing we're going to do is add external loads. And rather than adding a force, we're just going to include gravity in the whole thing, because not only does the motor have weight, but we've already designed that weight ahead of time. We've already assigned it, as well as the motor mount. We haven't calculated that weight or anything like that. So just creating gravity or just including gravity here is just going to do it for us. So everything's already set. So this is just static stress weight analysis. Can this motor mount handle the weight of this motor? Now we right click on mesh, create a new mesh. I prefer finer meshes because you get more detailed simulations. Doesn't really matter too much here because we're doing like super basic rigid connections, so we won't have to worry about that. As soon as you have that last step done, you can go to, what's it called, simulation again, run this study. This does take quite a bit of time, so I will unpause when it's done. Alright, so it finished. We can see the stress analysis of everything. Stress points are going to be typically around the surface where it's distributed, back plate of the motor, and then the edges of the motor mount. Any displacements? The front, but looks like it's only 0.01 millimeters of a displacement, nothing too extreme. Yeah, this would work, but it's also very expensive. Very expensive to do. So at this point, you can take what you want from this, redesign it however you want, and move on from there. Last quick rundown again of everything that happened. First thing we did was draw out designs, have an idea what we want, how we want it to be fixtured, how we want it to be mounted. Open up your motor. You can sketch directly on a saved copy of this and then delete the motor afterwards and just have the motor mount that surrounds it. Make sure you have clearances, make sure there's gaps so that it's better to be slightly oversized by like a couple millimeters than to be undersized. 1 millimeter should do fine. I don't think 0.1 is very good. I think maybe 1 millimeter of a clearance is way better. Or if you really want to play the safe side, maybe like I don't want to say 1/4 of an inch, but like maybe a 1/16 of an inch or something like that, something super small. After you design your motor mount, go to your assembly file, make sure you mate everything the way it needs to be, line it up the way it needs to be lined up in the scan file. It's called scan model. If you want to double check that, you can go here. I guess I can't show it, but you can go to the scan model, show it, line it up, and then make sure that if you go above, that nothing is touching or cutting into areas it shouldn't go to. Line everything up, made everything the way it needs to be. Make sure that the only fixed thing is the actual hood itself. That should be the only thing fixed. Go into simulation, static stress analysis, add material to your parts. Make sure you add contacts to your parts so that they don't blend in together. Add fixtures so that you know exactly where it's fixed and where everything's going to be, not deforming from. Like, where is it not going to move? What's going to be absolute? After that, you start adding contacts, saying, okay, this is connected here to that, this is connected to that, just all your connectors, all your rigid connections. Add gravity. If you want, you could also add an external force if you're planning to add more weight to this. And then create your mesh. And then run the study. That's pretty much it. Super basic, super quick. That was like 20 minutes long. You can skip through. But yeah, pretty much it. Thank you. Oh, always message me if you have any questions or if you're having problems. I can try to troubleshoot with you.